Hello, this presentation addresses the industrial controllers, part 3. So, the presentation is organized as follows. In the first part, I'm going to address the two-point identification method. Then I'm going to present an example regarding this two-point method. In part 3, I'm going to speak about another well-known method, it's the Cohen-Coon tuning rules. And in point 4, I'm going to present the IAE integral absolute error tuning rules. Is another method very well known proposed by Mario. So we are going to see, we haven't seen in the previous presentation, the tangent method, which is used to identify a first order plus time delay model from a step response. So now we are going to see another method which was proposed by Sanderson and this author, which is known as the two-point method. So what is how does it work? We apply a step in open loop to the manipulated variable of the process, and we observe the system output, which is for most cases, if the system is stable and not has oscillatory poles, so it is a sigmoidal shape or S shape, and from this shape we can extract the three constants for a first order plus time delay model: K, T, and L. DC gain, time constant, and time delay. So the procedure is like this. First, to obtain the system open loop step response. Then we have to determine the system responses in 2 points. When you reach 35.3% of the final value, and then store the time, this time corresponding to this point, and the time where the system reaches 85.3% of the final value. We are going to call it T85. So after we have these two values, we can then use the formula, the equations proposed by the method for evaluating the T and the L, the dead time. So we are going to see an example, and we are going to consider again the first order, a three-order pole in -1, this system. So the open loop response for this case, when the unit step, when this is equal to 1, the amplitude of the step is 1, and the step is applied in 0, you can see that it has a sigmoidal shape. And in green and red, you got the 2 points. The first point is we can see here that you can extract the output for 35%, and the time for 35%, in this case is 2.2 seconds. And the same thing for the second point, we call it the T85 for 4.8 seconds. The gain is evaluated as before, so the amplitude, the delta from the output divided from the delta from the input, and in this case is 1. As you can see, because both the input and the output is 1. So we can evaluate using the formulas the T and the L, and we got the first order plus time delay model identified with this 2-point method, with this one. And here T, we got here L. Okay, L and T. So now we are going to continue this example. We can do a simulation, for instance, using a Simulink model, applying a unit step both to the model, to the third order pole model, and also to the model that we identified just now with the 2 points method. So if you do this simulation and you compare the responses, you can see here in blue we got the step apply at 0, and then in black we got the system output, and in red, dashed red, you got the model output. So we still have an error here, but you can see from this point that the overlap is good, and in this part the model is not so good. And but you can compare this with the tangent model. So if you do the same thing, plotting a tangent in this point, in the inflection point, we got another model. We are going to call it here the tangent model, represented by this equation. And now if you now compare the two-point model response with the tangent model response and the system, the third order pole model response, we obtain the following plots. As you can see that there is, in this case, there is no comparison between the 2 points model in red and the tangent model here in black. So we can see that in this case the identification error is much lesser with the 2 point model than with the tangent model. Okay, this is with 2 points and this is with tangent. So based on the 2 point model, you can use any tuning rules. In this case, the Cohen-Coon tuning rules are well known, and so we can use this first tuning rule to determine the proportional gain, and this second to the iterative gain, and the same with the Marial IAE rules. So the KP in this case is this one, and the TI is this one. So comparing the two tuning methods using a step response, you can see that in red we got the IAE results, step response, and in black the Cohen-Coon. So we can see that the IAE has a better response than the Cohen-Coon, and we can do the same for PID controller using another tuning rules. And in this case, you can check this better. The response with the PID controller is this one. You can see that both in this case the IAE has a better response. Is not so faster in the beginning, but then it doesn't have overshoot, a higher overshoot as in the Cohen-Coon. Okay. So with this, I conclude the presentation. You can check the 2 points in the original paper and also in the book from Seaborg and Edgar and Mellekamp, Process Dynamics and Control. And if you want, you can also check the notes PID Control Simplified. Thank you for your attention.